really helpful if you wrote what all of this business was about on the board.
Wrote what it was about?
Yes. So your style is basically writing millions of equations on the board without actually writing words. And that's your style, and it's okay. But it might be helpful with titles of sections that might be helpful.
All right, I can see the point of what you're saying. Thank you. So, I suppose the reason why I don't is that it seems to me always that it takes me so long to write a sequence of English words. Also, I'm not the world's best speller.
Spelling is like, you don't have to worry about that. As long as we get the general idea of what you're trying to say.
Yeah. But apart from spelling, my handwriting isn't so great.
It's fine.
Those are equations, I know how to do them.
They're still basic characters. Look at your A and your B. Perfectly legible.
That's printing.
Yeah, and you'll recall that he struggled to write a B correctly in one of the other.
Yeah.
No, I would sort of second Catherine's opinion there, Kevin.
Thank you.
What's that?
It would be helpful for organizational purposes and for knowing where we are, because you do tend to go back and forth between the boards. So that might enforce a more logical flow to the stuff on the board.
All right, I thank you. I completely, I appreciate what you're
For how
saying.
many years now? You're probably not going to change.
Yeah, it's,
It's an old
is this
habit.
thing on or not?
It's on. It's on.
Okay, I will try. However, the English words on the page here are if, then, for, and then, operate.
Okay, put those on the board too.
MS's notation now, and now. That's not very helpful.
Not really. What would you have said if the camera was turned off?
All right, well, let's go on. Okay, here, hidden meaning.
Thank you.
That's beautiful.
And maybe I should say more.
Totally legible.
Indirect equation.
That's 2 words.
Okay, now, we've already seen that the m is the mass. Actually, it turns out that the m in Dirac's equation, in other words, if you have here I d slash minus e to the I theta m, the physical mass is the absolute value of m. So physical mass is okay, and I guess that's not. That may not be, that's not obvious from this, and it's not obvious from what I did there, but it's true.
So why do we even incorporate that phase factor into the equation?
Why what?
Why do we even put that phase factor?
We don't. That's why, but the point is that, I mean, you might sometimes see Dirac's equation with a plus instead of a minus. It's the same mass. Actually, now that I think about it, I'm certain this is true, that you can flip the sign of m and it's the same physical mass. Whether a phase is okay. That's my memory, but I haven't seen proof of this lately, so maybe it's not absolutely true. The reason why the sign of m doesn't matter is you see in these equations was m squared that turned out. All right, now let's consider Dirac's equation here. Gamma nu, say, I d nu minus e a nu minus m psi equals 0. And now what we're going to do is we're going to repeat the previous trick, but now with the electromagnetic field in here, and this is going to be more complicated. It's going to be then gamma mu I d mu minus e a mu plus m. All right. Yeah, sure. We don't have any pizza, but we ate whatever we swiped. So what we've got now then is I d mu minus e a mu, I d mu minus e a nu, gamma nu minus m squared psi equals 0. Okay, now there's a mathematical identity that's fairly simple to, you can just write it out. Little ab times big AB plus BA times BA. You can see that this is 1/2 the commutator of A with B times the anti-commutator times the anti-commutator of A with B plus 1/2 commutator of A with B, little a with little b, times the commutator of big A with big B. And in this particular case, what I'm looking at is the application then is the d mu gamma mu gamma nu plus d mu gamma nu gamma mu is 1/2 the anti-commutator of d mu with d nu times the anti-commutator of gamma mu with gamma nu plus 1/2 the commutator of d mu with d nu times the commutator of 2 gamma matrices. On the other hand, this is the same as that because the mu and nu are dummy indices. And so this is equal to 2 d mu, d nu, gamma mu, gamma nu. Okay, so altogether we get a 1/4. And so what that means is that from Dirac's equation, we get this expression. 1/4 the anti-commutator of d mu minus e a mu with I d mu minus e a nu times the anti-commutator of gamma mu with gamma nu plus 1/4 times the commutator of d mu minus e a nu with I d mu minus e a nu gamma mu minus m squared psi is 0. Okay. All right, well, you know that the definition of the gamma matrices is that the anti-commutator of 2 of them is 2 times the metric of flat space. And so what we get here is 0 is equal to 1/2 eta mu nu times, again, this anti-commutator. And now, a quarter gamma nu is, a quarter times the commutator is minus I sigma mu nu. So let me just remind you that one of the definitions, this is Schwarz's definition, sigma mu nu is I over 2 gamma nu. And so this thing, quarter gamma nu, is minus I sigma mu nu over 2. And again, the commutator d mu is the commutator of the covariant derivative.
So what the heck is sigma?
Sigma,
Besides the definition.
sigma, well, it's just a symbol representing the commutator. But remember,
Okay.
no,
I give up. I give up.
no, there's more.
Okay.
Remember the magic of the gamma matrices, namely that the commutator of two gamma matrices is proportional to the generator of the one of the generators of the Lorentz group. And in fact, the thing is I over 4 basically is the generator. And those generators then satisfy the algebra of the Lorentz group. And because we're writing it in this form, it's that rather overly impressive algebra which has so many terms, whereas the essential algebra that allows us to actually think is the one that involves J plus and J minus, and that's just 2 angular momentum. All right. Yeah, in fact, I have here, you'll be happy.
Oh, you do?
Yes.
You should put that on the board.
Okay.
There we go.
AKA J mu nu. Actually, it's 2J mu nu. With J over J. All right, now, to get along with some of this, what is this commutator? This commutator is very cute. It's I d mu minus E a mu, commutator I d nu minus E a nu. Well, it's of course minus I e d mu a nu plus I e d mu a mu. And of course the derivatives commute, the fields commute, and so the only thing that's left is that, and that is minus I e f nu. So this is the Maxwell field, the electric and magnetic fields of and this thing, these are just the anti-commutator covariant derivatives with an eta mu nu and the 1/2, and altogether then, if you boil that down, what we get is 0 is equal to minus d mu d nu minus E over 2 sigma mu nu f mu nu minus m squared. What happened to the noise?
It's the blessed silence.
It was actually comforting in a sense, having all that noise.
In what sense is it comforting?
Oh, I don't know. It's at least a sign of life.
What about us sitting here in the seats of comfort?
Well, that's a more dramatic and impressive sign of
Thank you.
You're welcome. Okay, so what do we get? Getting rid of the minus signs, we have plus, plus, plus. And so this, you recognize if you set the electromagnetic field equals 0, this is just the Klein-Gordon equation. But now you see these are covariant derivatives. So if psi were just 4, I mean it is 4 fields. So apart from the sigma mu nu term, what it's saying is that it's 4 fields, each of which satisfies the same equation as a scalar, as in a scalar field in scalar electrodynamics, because that's that equation. The new thing is the sigma mu nu f mu nu, which is rather a nice term, and we can, and in particular we get something else, namely the t slash squared is d mu plus e over 2 f mu nu sigma mu nu. Now, remember that these f's, F0i is the ith component of the electric field, Fij is minus epsilon ijk bk, where that's the magnetic field. And of course, there's always an ambiguity in what you call F mu nu. Here, F mu nu is d mu a nu minus d nu a mu. And half the time people write it with a minus sign here and a plus sign there. And that's just the vagaries of notation. Now, in Schwarz's notation, gamma 0 is 0, 1, 1, 0, where these are all 2 by 2 matrices. And gamma is 0, sigma, minus sigma, 0. In Weinberg notation, all of these, each of them has a minus I in front of it. And that flips the metric. Why it's minus rather than plus I guess he wanted something else to work out nicely. Probably use the Dirac equation. Because I think his Dirac equation is just d slash plus m psi. Okay, what's this Sij? These now are the are 2 I'm talking about 1/2 sigma mu nu, or sigma ij. And so this is then I over 4 gamma I gamma j. Okay, well, we can work out what that is. Namely, Sij is then I over 4, and it's 0 sigma I minus sigma I 0, 0 sigma j minus sigma j 0, minus the same things in the opposite order. And I guess I should skip. You want? Well, maybe we should see. So what? We'll see. Maybe I'll do this after all. And if you work this out, then it's I over 4 minus sigma I sigma j 0, 0 minus sigma I sigma j, and then minus sigma j sigma I minus sigma j sigma I. Okay, well, if you combine these, what you see you've got here is minus I over 4 times the commutator sigma I with sigma j, and then minus, well, no, plus sigma I sigma j. And now the sigmas, of course, well, the generator is the Lorentz group, so you have sigma I over 2, sigma j over 2, is I epsilon I j k, sigma k over 2. So that means the commutator of sigma I over sigma j is 2 epsilon I j k sigma k. So this is minus I over 2 epsilon ijk sigma k 0, 0, sigma k. Oh, there's an I here, and that with the minus I gives you an actual 1/2. All right, so that's what Sij is. S0I is easier. S0I is a half sigma 0I, which is I over 4 gamma 0 gamma I. And this is then I over 4, 0, 1, 1, 0, 0 sigma I minus sigma I 0 minus 0 sigma I minus sigma I 0, 0, 1, 1, 0. And if you work that out, that's minus sigma I plus sigma I. And so this turns out to be I over 4 minus 2 sigma I 0, 0, 2 sigma I, or minus I over 2 sigma I 0, 0 minus sigma I. So that's what that looks like. And now we can take these things and put them in this equation here, and in particular attach them there, and then what we find is d mu d nu plus m squared plus e over 2 f0I sigma 0I plus e over 2 fi 0 sigma I 0 plus, well, I guess these are all anti-symmetric, so I guess this is kind of silly, in fact. I wrote it out explicitly, but it's just E plus E. Well, in this case, at the Fij, sigma ij, that's why I did it. No sum here. So in other words, you don't.
Are we breaking the Einstein summation notation right now? For realsies?
All right, okay. That way was okay, but now I'll put this. Well, it's all right. Let's just do it that way. I think this is right. Psi equals 0, and what this turns out to be then is d mu. I said d mu d. There was an eta here, so this is d mu plus m squared minus IE dotted into sigma 0, 0 minus sigma plus epsilon ijk over 2 Fij sigma k 0, 0 sigma k. And then psi.
Okay, I now have to ask, how big are the sigma matrices?
2 by 2.
They're 2 by 2.
Well, that's the Pauli's. Well, yeah, the sigma
Okay.
with one subscript is the Pauli.
Okay, so then what?
Yeah, you're
what the
absolutely
heck
right.
does
This is a
that
terrible,
What the heck
terrible
does that
notation.
gamma mean then?
Gamma is 4 by 4,
Okay,
and this sigma is 4 by 4.
I see.
So this is a stupid notation. This Pauli is 2 by 2. This is 4 by 4.
You said it was stupid, I didn't say it was stupid. Want that on the record.
So, we've got this thing epsilon ijk Fij, but we have that formula relating F to B. So this is actually minus epsilon ijk epsilon ijl BL. Now, if you think about this, what is the case? Well, if I and j are 1, 2, then k has to be 3, also L has to be 3. But if ij are 2, 1, it's the same thing, L has to be 3. So altogether, this is minus 2 bk. And consequently, the Dirac equation implies d mu d mu plus m squared minus I e dotted into sigma 0, 0 minus sigma minus b, oh, there's an e here, sure. Minus EB dotted into sigma 0, 0 sigma psi. And so that's what the Dirac equation implies. And now you might say, how do you get down to something that's more recognizable? In other words, how do you take the non-relativistic limit? Well, you let psi of x be e to the, say, minus I script d plus m t times psi of x written slightly differently. And in other words, this is the part of the energy that doesn't involve the rest mass of the electron. And then what you've got here is 0 equals minus m plus e squared plus m squared, and then you can have a Laplacian from that. Then you've got various terms that the Dirac field shares with scalar electrodynamics. And then I want to emphasize the B term. Actually, yeah, that's right. There must be a B there. And so then when you divide, first of all, the m squared terms cancel. And then you have a minus 2m. You divide through by minus 2m, and you have something like this. 0 equals e minus Laplacian, well, it's actually, it should be a plus. At least, all right, plus dot dot dot, and then finally plus b over 2m, eb over 2m, sigma 0, 0, sigma psi. So what this has done is, in other words, the equation would be E equals minus Laplacian over 2m, and so this probably should be a minus sign also. Might be a plus sign. Well, depends on what you mean by the E, whether it's plus the proton or the electron. So, in any event, what this shows you is that if we look at the magnetic moment, it's E over m, B dot sigma over 2, effectively, if we just look at it as two components. And this is the spin. Notice this is twice the Bohr magneton, and so that's that factor of 2 that comes in predicted by Dirac and the Dirac equation. All right, yes, question, and shall I show you a fructose-free?
Finally break down and have the fructose-free candy. Shouldn't that be E squared?
Well, I actually asked my wife to get these, so I went and got them last night.
So should that be E squared in the bottom there?
B squared?
No, E, but the script, yes, that one.
Oh, there is an E squared, but E squared over 2m is very small. We divide through by 2m. Okay, so that's some of the relations I wanted to show. Now I'm going to do something different, and so previously I showed you why in two-component language the action density for a left-handed field and a right-handed field, why they were Lorentz invariant. And I was doing that in terms of the Dirac's point of view and actual unitary transformations. Schwartz takes a more algebraic approach, and I think that that's worth seeing also. And in fact, it's in a Dirac context as opposed to a two-component context. So let's maybe go through the whole business. Let's just remind us of some things. Gamma mu plus gamma nu is 2 eta mu nu. Okay, now what this really means is that we have subscripts here. That's what that really means, okay? In other words, this is a 4x4 identity matrix, which I often left out. I just said it was 2 eta mu nu. I meant 2 eta mu nu times I for the identity. So maybe I should write down here Lorentz transformations. In Dirac notation. Now, these generators of the Lorentz group, I over 4, it's gamma, the commutator of gamma mu with gamma nu, so it's gamma mu AC gamma nu CB minus gamma nu AC gamma mu CB. Okay, now suppose we have an expression like this. V squared or V mu. So we can think of this as V mu, eta mu nu, V nu, and we can think of this as 1/2 V mu, anti-commutator of gamma mu with gamma nu, V nu. And so we can think of a Lorentz transformation, a spin Lorentz transformation times a gamma mu spin Lorentz transformation what is that? That is a vector Lorentz transformation, mu nu, gamma nu. It looks like this. Yeah, that was a new, well, sub-vector sub nu.
Kevin, do you mind if the high schoolers come watch the lecture?
Anybody?
You can come in. He says yes.
Okay,
Go
so
in. You have to commit. Make a decision. Commit.
write out all the indices. Then what we got is lambda inverse spinner. Let us say dA gamma mu AB spinner BC. This should be lambda V mu nu gamma nu DC. So this is what we expect. My goodness.
Yes! We have a question.
What does that mean?
Yes! You're so smart. Such a good question.
Where? All right. Students who ask questions get money. What I'm describing is the algebra of Lorentz transformations of Dirac fields, and how the four-component notation, Dirac notation, is related to the vector notation that one is more familiar with.
Hi, high schoolers.
High school students are gonna understand. Okay.
That was an you should write that summary on the board. So there's space up in the corner there.
All right, now let's look at some of this. In particular, that what do we have here? We have gamma mu, gamma nu, 2 eta mu nu. And what does that mean? That means that gamma 0 squared.
That high schooler's question was actually an appropriate one, though, wasn't it?
It means that gamma 0 squared is equal to 1 in the sense of a 4x4 identity matrix. It means that gamma I squared is -1, again as a 4x4 identity matrix. Because this says gamma I squared is 2 eta II, and eta II is -1 in Schwartz length. Okay. And what does this tell us? This tells us that the eigenvalues of gamma 0 are, or more generally the singular values of gamma 0 are plus or minus 1. And so gamma 0 is Hermitian. And on the other hand, these guys are anti-Hermitian. And in fact, we saw that because this, in the particular notation that we prefer, Weil's notation, basically, gamma 0 is 0, 1, 1, 0, so that's obviously Hermitian, whereas gamma was 0, sigma minus sigma 0, and that's clearly anti-Hermitian since the Pauli matrices are Hermitian. Okay, and so we have gamma 0 dagger equals gamma 0, gamma I dagger is minus gamma I. All right, now I want to say something about how what S looks like, and so let's focus on S mu nu. In particular, S mu nu adjoint. Well, this is I over 4, gamma nu, adjoint, and that's minus I over 4, gamma nu adjoint, gamma mu adjoint. All right, let's see, what is, well, we can obviously flip this, I over 4, gamma mu adjoint, gamma nu adjoint. And so if mu and nu are both space, then we get two minus signs here because, in other words, gamma I dagger is minus gamma I, so Sij adjoint is just Sij. On the other hand, since gamma 0 is Hermitian, we have Si0 adjoint will have one minus sign and the other one will not have a minus sign, and so we'll get minus Si0. So this tells us the generators of rotations, which are the Sij, are Hermitian. So rotation, gens, Hermitian, and these are the boosts, not Hermitian, so anti-Hermitian. Which is what we already knew, but it's nice to see it in this particular way. Now, let me just go through something in detail. Gamma 0, gamma I, gamma 0. What is this? Well, gamma 0 anti-commutes with gamma I, so this is minus gamma 0 squared gamma I. Gamma 0 squared is 1, so this is minus gamma I. And that's also gamma I adjoint. On the other hand, gamma 0, gamma 0, gamma 0, well, this times this is 1, this is just gamma 0. And that's also gamma 0 adjoint. So what this tells us then is that gamma 0, gamma mu, gamma 0 is gamma mu adjoint. So gamma 0 is a hermitizing matrix.
Sounds like hermitizing is actually a real word.
No, well,
If you use it enough, it'll show up in the dictionary. It's okay.
all right.
Wait, but
Oh, you get a you should get another candy for your suggestion. Here. All right.
Wait, but so gamma 0 is related to the time-like components of these things?
It's the time-like gamma matrix, yeah.
Yeah. So physically, we're kind of connecting like transformations in time to taking Hermitian conjugate, roughly speaking. In what sense?
I don't know. There may be something there, but I wouldn't bet my life on that. But it may be something there, you know, I mean, who knows. All right. Okay, so, all right, so we found that. Now, let's consider this. Gamma 0, S mu nu, adjoint gamma 0. All right, what's that? Well, that's gamma 0, I over 4. Remember, we sort of did a double trick here. S mu nu adjoint equals blah, 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 I over 4 gamma mu adjoint, gamma nu adjoint. And then a gamma 0. Now, we can pop two gamma 0s into the middle there because gamma 0 squared is 1. And so what we have then is I over 4 gamma 0, gamma mu adjoint, gamma 0, gamma 0, gamma nu adjoint, gamma 0. But gamma 0 is the hermitizing matrix, and so it turns gamma mu into gamma mu adjoint, or if you do it again, it turns gamma mu adjoint into gamma mu. And so this is then I over 4 gamma mu, gamma nu, and that's S mu nu. So the key thing here then is that the adjoint of the Lorentz generator with gamma zeros on both sides is the Lorentz generator itself. And that leads to a very nice relation, and that'll be basically the last thing we'll do today in this class. Namely, let's consider gamma 0 some spinor Lorentz transformation gamma 0, and we'll adjoint the whole thing. Okay, well that's the same thing as gamma 0, e to the I theta mu nu, S mu nu. So lambda, the spinor Lorentz transformation, is an exponential, the thetas times the generators, these being 4x4 matrices. And now we're adjointing the whole thing. So there's an adjoint here in the gamma 0, but the gamma zeros don't care about being adjointed. All right, so this is gamma 0. No, hold on. The gamma 0, you know, whenever you have something whose square is 1, you can just pop it into existence any way you want. So you can imagine this thing as a power series, and it has a term theta s to the 14th. Well, let's just do theta s squared. So you have gamma 0, theta s, gamma 0. So you can write that as gamma 0, theta s, gamma 0, theta s, gamma 0. So this thing is the same thing as E minus I, gamma 0, well, theta, the thetas are real, gamma 0, S mu nu adjoint, gamma 0, all in the exponent there. On the other hand, we've seen that this structure is just S mu nu. So this is E to the minus I, theta mu nu, S mu nu. And this then is lambda S inverse. Okay, now why do we care? Well, we care because it lets us see clearly from an algebraic point of view, rather than from an operator point of view, which I did in class. And, what we see is this: psi dagger, gamma 0 psi, under Lorentz transformation. Well, this would be psi dagger, the Lorentz transformation adjoint, gamma 0, Lorentz transformation psi. And, all right, let me make sure I've got this straight here. Right. So what I want to do is write this as psi. Right, okay. So gamma 0, lambda s adjoint, gamma 0, lambda s psi. All right, now if we focus on this part, we see that's the same thing as adjoint, that's the same thing as And so that's lambda S inverse. So this is psi dagger gamma 0 lambda S inverse lambda S psi, which is psi dagger gamma 0 psi. So that's why why this structure is Lorentz invariant. This, of course, is the Dirac mass term, which is often written as just psi bar psi. And to make it a mass term, well, you multiply it by a mass. And that's why that's Lorentz invariant. What I showed in class last week was why the kinetic term was actually invariant, as well as why this is invariant. But I thought it was good to see this, even though it's not the whole picture. And what's really going on here in a different point of view is this is C zeta, and then 0, 1, 1, 0, C dagger, zeta dagger. That's what psi dagger gamma 0 psi is. And so this is actually C dagger, zeta dagger, C dagger. And so this is C dagger, oh, I've got it backwards, don't I? This is zeta. C dagger zeta plus zeta dagger C, and there's no dagger here. And you see then this is a left-handed field, the adjoint of a right-handed field, adjoint of a left-handed field. And I showed you, I think, that those were invariant. One of them is e to the minus z dot sigma, and this one, the other one, is e to the z star dot sigma. And so when you take the adjoint of that, you have e to the z dot sigma, and the two are, one is the inverse of the other. So things are really simpler in the two-component notation. All right, I think we're basically done with chapter 11, so we'll start, I guess, chapter 11 next time. And eventually we'll get to quantum electronics.